molecular arrangement is how individual atoms in a molecule orientate themselves geometrically to give an overall picture of what that molecule is shaped like. And this is going to be very important in organic chemistry because many reactions will or will not take place depending on the arrangement of those atoms in that molecule. And it will be especially important in biological sciences because almost everything in the body reacts like with locks and keys. One biomolecule has a particular function and it will work like a key in a lock to do something. If it does not have that particular shape, it will never happen. And in fact, many genetic disorders are of that kind of nature, where it's only a slight variation in a biomolecule, but only a slight variation in the shape of a key will cause it not to work. And if there is a slight variation in that biomolecule, then whatever that biomolecule's function was, it can no longer accomplish. So these are important. And a good way of getting an estimation of what the molecular geometries will be is to use the valence shell electron pair repulsion model. And this is a very simple model. It just takes into account that the electrons are going to try and repel each other as much as possible. So what this model does is that it just maximizes the distance between all of the electron pairs in order to minimize the electron repulsions between each other. So if I have a central atom and I only have two electron pairs, that's very simple. They just go to opposite ends. And then when I have three, they adopt whatever shape that would maximize the space between the electron pairs. And in this case, it's 120 degrees for 3. This is as far spaced out as they can be. When I have 4, it becomes a three-dimensional shape. This is tetrahedral geometries. This is 109 degrees or something like that between all of them. Then when I have 5, I have this double-sided triangular pyramid, and then for 6, I have a double-sided square pyramid. And that's all there really is to it. It's quite simple. They just get as far away from each other as possible. Now, the only other thing that needs to be mentioned is what happens when I have something like water. Or first, let me think of methane. Methane is very simple. It has 4 valence shell electron pairs, so it would have dropped tetrahedral geometry. But what about water? It has 2 bonds. So many people might think to give it linear geometry, but it in fact has bent geometry. And the reason that is because it also has 2 lone pairs, 2 non-bonding pairs. So it in fact has tetrahedral geometry. 2 of these would be bonding pairs, and then 2 of these would be non-bonding pairs, lone pairs. Here's methane with 4 bonding pairs. No lone pairs. Here's NH3. It has 3 bonding pairs and 1 lone pair. So it also has tetrahedral geometry. But since one of these is a lone pair, most often people think of it as this pyramid shape. But it's okay to think of it as this tetrahedral shape. In fact, I always think of it as a tetrahedral shape. Some people will think of it as a pyramid shape. But in fact, that non-bonding pair is still there. And very often, the non-bonding pairs are the most reactive in organic chemistry. At least that's what I've certainly come to see, that they are generally the more reactive. And here is water. It has two bonding pairs and two lone pairs. So it has a tetrahedral geometry as well, but more often than not it will be drawn as this bent shape. And in most books they'll not include the non-bonding pairs. If it's a bent shape, they'll draw it as a bent shape even though it's technically a tetrahedral, but in order to save space they almost always end up drawing these, and by that point everyone knows about the non-bonding pairs. So that's basically the valence shell electron pair repulsion model. It's just maximize